As mentioned, I really forget to share the question on VLE. I will do it shortly later on, but it's okay. As I explained the tutorial, the questions are also there, right? So this is the question for tutorial. As you can see, I discuss step by step, right? So again, I think it's quite impossible for us to do together. Kalau physical, I think it's possible, but online, I think it's a bit impossible for us to do together. So what you do is that for the next 1 hour, 1 hour plus, you understand first the steps. At least you understand the step, because as mentioned, reaction, the challenge is not really about solving. It's actually understanding the question. So when you don't understand or you misinterpreted the question, that will cause you not to be able to solve. Okay, so you just listen first. Later on, when you have time, okay, you can look back the video. You can actually do the question slowly. So even when I upload the question on VLE, I provide you the final answer as well. So at least you know you are solving it correctly or not. Okay, so you can do it later on, but let me explain first the question. All right, so we will start chapter 2. As I said, we don't have question for chapter 1, we only have question for chapter 2. So later in test 1, I will have one question from chapter 2, one question from chapter 1, chapter 3, sorry, one question from chapter 2, one question from chapter 3. Okay, so let us focus on the question. All right. Okay. So the first question, let me make it even bigger. Okay. So the first question is that 3.5 mole dm cube of pure A enters the reactor at the rate of 10 dm cube per second. Okay. So at this stage, okay, at Chapter 2 questions, even for test 1, it's very important for you to really know the number given to you represent what. Okay, so that is the challenge. Let's say you misinterpret the information. Let's say I give you concentration, but you interpret it as molar flow rate or volumetric flow rate. So that is the error that you cannot make, because once if you identify the number, definitely your entire question will be wrong. Okay, so you must really understand what the number represent. Okay, so first of all, we just start first with the first sentence, right? Okay, so they say 3.5 mole per dm cube. So by now you already learned, right? Mole is molar, dm cube is volume. Okay, so you always convert the unit to dimension. Then you can guess what does the parameter means. Okay, so mole per dm cube is mole per volume. You already learned, right? Mole per volume is surely concentration. Okay, there's no other parameter that will have mole per volume except concentration. So you know that it's definitely C, because concentration is represented by C. But you also understand that the concentration is specific to which chemical. Is it reactant? Is it product? Because in this reaction, you have 3 compounds. You got A, you got B, you got C. Is it concentration of A, concentration of B, or concentration of C? So read back the question. They said that 3.5 mole dm cube of pure A. So it's definitely for concentration of A. Okay, so you know that it can be either Ca or Ca naught. So what's the difference? Ca naught is the initial concentration of A before the reaction occurs. Ca is the concentration, outlet concentration, or the concentration during or after reaction. So now you have to determine the next step, Ca or Ca naught. So go back to the question. This says enters the reactor. So meaning that it's the concentration before the reaction takes place. So it's definitely Ca naught. Okay, so you know the first information, Ca naught is 3.5. So this is the part that you cannot make mistake. Let's say you write it as molar flow rate, you write it as volumetric flow rate. So you are already wrong at the very first sentence. So I have to highly emphasize at this stage, please already identify the unit and the dimension and the symbol that represents the unit and the number, sorry. Okay, so we go to the next one. This is at the rate of 10 dm cube per second. Okay, so next one, dm cube per second. So dm cube is volume, second is time, right? So volume per time is definitely volumetric flow rate. Volume per time is definitely volumetric flow rate. Okay, so again, they say enters the reactor, right? So it definitely is epsilon naught. So epsilon naught is 10 dm cube per second. So you know now that For the very first sentence, I only know CA naught and epsilon naught. Okay, that's all that I have, right? So next, they give you the chemical equation, A produce B and C. Okay, there's only one reactant and they say pure A, meaning the A that enters are 100 mole percent of A. Okay, then they give, by using the data, calculate the reactor volume for the scheme below. Okay, so they give you the table, right? So you have learned in chapter 2, right? When we are given the information of X and minus RA, we can use this to calculate the volume of the reactor, PFR or CSTR. Okay, so remember this information can be in the form of table or it can be in the form of a plot. Okay, so we learned the Levenspiel plot, right? But this question is just in the form of table, right? So we understand the table. The table says that, okay, let's say if my conversion is 0, my minus RA is 0.053. When my conversion 0.1, my minus RA is 0.052, so on and so forth until the end. Okay, so by this information, let us solve the question, right? Okay, so first of all, if you realize, okay, in our calculation in chapter 2, we will definitely in the formula will have FA naught. Okay, if you remember FA naught is initial molar flow rate of A. Okay, again, FA naught is initial molar flow rate of A. So if you remember the equation, PFR or CSTR, single or series, all of them will have FA naught. But you realize that in the questions, FA naught is not provided. Okay, so you must understand engineering question, especially at semester 4, is no longer straightforward. Okay, meaning that sometimes you may need to find some information or you may need to calculate first certain information without being told, without being asked. But you have to know that in the formula, I have FA naught. So meaning that if my question does not have FA naught, I have to find it first. Okay, so in this question, they do not provide you FA naught, but they do inform us CA naught and epsilon naught. Okay, so again, CA naught concentration, epsilon naught volumetric flow rate, FA naught molar flow rate. Okay, so if you remember, I have taught you the correlation between these three. Okay, the original one that I taught you is actually CA naught equals to FA naught per epsilon naught. Again, I repeat the original equation that I teach you in chapter 2. So let me check. Let me show you. Just in case you can't, just in case you cannot remember, let me show you back again. Is it chapter 2 or chapter 1? Oh, I think it's chapter 1. So hold on. Let me check chapter 1. Reaction. Let's reaction. Lecture. So that at least you are familiar with the equation. Okay, so in chapter 1, let me check. This one. Okay, so you remember in chapter 1, I already taught you, right, the correlation between CA naught, FA naught, and epsilon naught. So the correlation given is CA naught. Okay, this one you have to remember because this is not provided to you. CA naught is equal to FA naught divided by epsilon naught. Okay, so in our question, they gave us CA naught, they give us epsilon naught. So of course, FA naught will equal to CA naught multiplied with epsilon naught lah. Okay, so again, they give us CA naught is equal to FA naught per epsilon naught. Therefore, FA naught equals to CA naught multiplied with epsilon naught. So that's what I did in the question in the tutorial. So that is what I did in the question. You can see that, right? I hope that I don't get you confused. So you can see here, FA naught equals to CA naught multiplied with epsilon naught. Okay, again, let's say you get confused. Should I divide? Should I multiply? You can also use what you learn in CPP and also something that you have learned in many courses. You can try to do the unit cancellation. So sometimes it's good to include unit in your calculation because you can do unit cancellation and you can check whether is it correct your final unit. So let's say your final unit is the unit that you want. Most likely your calculation is correct. But let's say when you cancel the unit, you did not get the unit that you want. So meaning to say that your formula has some errors and you need to check back. So for example, in this case, let's say I assume FA naught is equal to CA naught multiplied with epsilon naught, right? Okay, so CA naught is 3.5 mole per dm cube. My epsilon naught is 10 dm cube per second. One is concentration, one is volumetric flow rate, right? You can see that I can cancel my dm cube and dm cube. Then I'm left with mole per second. So again, you check back. What are you calculating? You're calculating FA naught, right? You're calculating the initial molar flow rate. So initial molar flow rate, the unit will definitely be mole per time. Okay, so your unit for molar flow rate, initial molar flow rate will definitely be mole per time. So you get the correct unit, you get mole per second. So very likely your formula is correct. Okay, so FA naught is 35 mole per second. So again, for those who wonder why do we find FA naught, because if you remember in chapter 2, the design equation to find PFR ke CSTR, they definitely will have FA naught. Okay, so although the question did not ask you to find, but you have to know by yourself, if my formula have FA naught, I have to find FA naught first. So even if let's say you cannot answer the question, if it's me, you do try to solve at least some part of it. Let's say you find FA naught, you already get at least 2 marks, you know. So you may not solve the rest, but you at least get some marks from solving it, because it shows me that you know that FA naught can be found from CA naught and epsilon naught information. All right. So we are done. We haven't even go to the question, right? We just solve first the initial information. Okay, so let's go to question A. So question A says that they ask you to find the volume of a single CSTR with conversion of 80%. Okay, so again, I keep telling you, the conversion can be given to you in the form of percent or fraction. Regardless of what, when you are doing the calculation, the percentage must be changed into fraction. Okay, so calculation, even if they give you conversion in percent, you have to change into fraction. So let's say my x is 80% conversion. In terms of fraction, it becomes 0.8. So we have learned, right? Conversion, we use x for conversion. So x is 0.8 and our FA naught, which we have find earlier on as 35 mole per second. So this is the two information that I have for me to solve, right? So then what you do? You can go to the list of equation. As I mentioned, you don't even have to memorize, but you have to really know what equation to use. So for single CSTR, to find the volume, the formula is volume CSTR equals to FA naught X per minus RA. Okay, so again, that minus RA is at my conversion 0.8. Okay, so when I put the subscript 0.8, it's not mean that you multiply 0.8. It's just to indicate to you that you have to use the minus RA when my x is 0.8. So you have to go back and check the table. Okay, so let us solve. So FA naught is 35 mole per second as we calculated. The x is 0.8. The minus RA, as I mentioned, you go to the table, you check. When my conversion is 0.8, my minus RA is 0.013. Okay, so I will substitute my minus RA with 0.013. And if let's say you are not sure, you can do the unit cancellation, although in this case, the formula is given to you, right? So without the unit cancellation, you should be able to solve it. So you will get the volume of the CSTR, the single CSTR as 2,153.85 dm cube. So again, some may ask, what is the significant figures necessary? So for me, I'm okay. You want to put it 2, you want to put it 3, you want to put it 4, I will still accept the answer, because I will also, let's say you submit me the answer, I'll also recalculate back using your numbers to check whether it's correct or not. So you don't have to worry too much on the significant figures. You will not be punished for the amount of significant figures. All right, so done for single CSTR part A. Okay, so that is very easy. I assume that this is not be a problem for you. Right, so let us go to second question, single PFR. Now we're doing PFR with the conversion of 80%. Okay, so now this is single PFR of which they are converting from 0 to 0.8. Okay, so if you remember the formula for PFR is slightly different, right? So the volume of PFR equals to FA naught, integrating from 0 to 0.8. So integrating from 0 to 0.8. Hold on, let me check. I need to use the pen. You know, I scared that you cannot see it. Wait, I just realized I did not use the pen. I worry that you may not be able to see where I put it. All right, okay. Okay, so the formula is, okay, I will make it like this. Okay, so the formula is volume PFR equals to FA naught 0 to 0.8 dx per minus RA. Which I like to use the pen, but I cannot find the pen. Because it's not like PowerPoint, right? So that is the issue. Now, I think should be okay, right? I hope that you can catch up. Okay, so then you remember that because of the integration, we cannot solve the integral, right? We will solve the integral using Simpson 1/3 rule. So you remember that for the question where we have integral part for PFR, we will solve it using Simpson 1/3 rule. So even the Simpson 1/3 rule is provided to you, but you have to understand how do we use the Simpson 1/3 rule. So the formula is given as FA naught delta X per 3. Okay, so again, Y per 3 because Simpson 1/3 rule, 3 point. So it's per 3. And behind you will have 3 point. So the first point is 1 per minus RA at my conversion 0. Why at conversion 0? Because for the single PFR, the bottom limit is 0 because the conversion started from 0, right? Single PFR, right? And the upper limit is 0.8 because that is my highest conversion that I achieve. So the first point will be 1 per minus RA when my X is 0. The last point is 1 per minus RA when my X is 0.8. Let me point out here. Oh, sorry. So, kejap hold on let me, hold on a while Okay, so the first point is 1 per minus RA when my X is 0. My last point will be 1 per minus RA when my X is 0.8. This is very important because when I provide you the Simpson 1/3 rule equation, it's a general equation. You have to know by yourself what is your bottom limit and upper limit. Okay, or else you will not know what point you will use the number. Okay, so the initial limit was 0. So the first point, 1 per minus RA at 0. My last point is my upper limit, which is 1 per minus RA at 0.8. And the middle one, okay, the middle point is 4. So the 4 is a formula. Okay, the formula says the middle one will be 4 per minus RA at my middle X or my middle or my mid X. Okay, so meaning you say, if your initial X is 0, your final X is 0.8, so your middle X will be 0.4. Okay, so again, this is the risk of this question. The 3 point, you must really know what is my bottom limit, my upper limit, and my middle limit. So the middle one is the one that you have to know by yourself. You have to calculate by yourself, right? So once you have established the formula, then now you can substitute the value. Okay, so the volume of PFR equals to FA naught 35, which we have calculated. So the FA naught that you calculated initially, right? Because they give you the initial information, right? So you use the information, you already calculated the FA naught, you can use the FA naught. Okay, then next, delta X per 3. So how do we calculate delta X per 3? So again, delta X is the gap between 0 to 0.4 or 0.4 to 0.8, or the difference between 0 to 0.4 or 0.4 to 0.8. Either one, the gap is still 0.4, right? So delta X is 0.4 divided by 3. So again, I keep emphasizing delta X is not the middle X. Delta X is the difference or the gap between initial X to middle X or middle X to final X. Okay, then next, the 3 points. So the first point must be 1 per minus RA when my X is 0. So I will go to the table. You can see when my X is 0, my minus RA is 0.053. When my X is 0.4, my minus RA is 0.040. When my X is 0.8, my minus RA is 0.013. Okay, so these 3 points, you will just substitute the minus RA value. So you see 1 per 0.053, 4 per 0.040, 1 per 0.013. Okay, so once you substitute all the value, okay, then you can calculate the volume. So the volume will be equals to 913.69 dm cube. Okay, so that's the solution for question number 2, 1A and 1B, right? So I give you maybe 1 minute just to look at it, okay, before I proceed, because I do not want to text you so much. So I give you 1 minute. You can look back at the solution before I proceed to the next question. Okay, so 1 minute for you guys to look at it. Okay, right? So hopefully you are okay with question A and B. So it's quite easy question, all right? So let us go to question C. Okay, so now question C, we already go into reactors in series. Okay, so the question says, calculate the volume of the reactor if two CSTR are connected in series with an intermediate conversion of 40% and a final conversion of 60%. Okay, so now we are talking about reactor in series, and in this case we have two reactor in series. So you remember I told you when we have two reactor in series, you will have separate conversion, meaning you have conversion for the reactor 1, conversion for the reactor 2. So in this case, the first CSTR, they are converting from 0 to 0.4. Okay, meaning your X1 is 0.4, or we call it intermediate conversion, right? Okay, then next, for the second reactor, they are converting from 0.4 to 0.6. So your X2 is 0.6. So you remember I taught you conversion is continuously increasing. They are never reset. So meaning that the more reactor I use, the higher the conversion will be. So the first reactor, they are just converting from 0 to 0.4. When it goes to the second reactor, it further increased from 0.4 to 0.6. So it's very important to know that the conversion will keep increasing with more reactors. And then again, FA0 is still the same, okay, because we are still using the same concentration, same volumetric flow rate, your FA0 will not change, okay? So again, for those I'm confused, why do we keep using the same FA0? Because The initial information given to us was Ca naught and epsilon naught, right? Concentration and volumetric flow rate. As long as the concentration and volumetric flow rate does not change, your molar flow rate also will not change. So you can still keep using the same Fa naught. Okay, so how do we solve this? So again, you go back and check the formula. When we're talking about reactor in series, there will be two different formula for reactor 1 and reactor 2. So you must remember that you are calculating two reactor volume, which is reactor 1 and reactor 2. Okay, so you must calculate both reactor volume and they comes with different equation. So when you check the list of equation, for the first reactor, the volume is given as Fa naught x1 per minus Ra volume of CSTR1 equals to Fa naught x1 divided by minus Ra, where at my x1. Okay, again is minus Ra at my x1. Okay, so how do we calculate? So the Fa naught is 35, it's still the same. The x1 is 0.4, okay. The x1 is 0.4 and then minus Ra when my x is 0.4. So again, you go to the table, you can find that when my x is 0.4, my x1, my minus Ra is 0.040. So you just replace with 0.040. So you will get the volume of your first CSTR as 350 dm cube. Okay, so again, it's not difficult, I can admit that, but you may get confused with the formula, right? So make sure you really know which formula to be used. Okay, so let us go to the second reactor. So the second reactor, I has mentioned, the equation has been changed. Okay? We have learned last Monday, right? I already taught you how to derive. Okay, it's also okay if you can't remember, but you must know what equation to be used. So for the second reactor, the volume is equal to Fa naught in bracket is now x2 minus x1 per minus Ra at my x2. So just remember, for the first reactor volume, the minus Ra at x1. For the second reactor volume, the minus Ra at x2. Okay, so you remember that, then you are fine. Okay, so Fa naught is still 35 mole per second. That's why we said why we keep using the same Fa naught regardless reactor 1, reactor 2, because as I said, conversion does not reset. It's based on the very initial Fa naught. So regardless you go into 10 reactors, you will still use the same Fa naught, which is the first initial molar flow rate that enters the first reactor. Okay, so Fa naught is still the same, 35. Then x2 is 0.6, x1 is 0.4. Okay, so that is from the calculation. And last one, minus Ra at 0.6. So you go up, you check the table at 0.6, my minus Ra is 0.025. So again, I will replace 0.025, okay, for my minus Ra, and you get subsequently the reactor volume as 280 dm cube. So don't forget, when you have 2 reactor in series or even 3 reactor in series, you have to calculate the volume of each of the reactor. So in this case, if I want to achieve 40% conversion in my first reactor and 60% conversion in my second reactor, the first reactor volume must be 350 or at least 350 dm cube, and my second reactor volume must be at least 280 dm cube, or else you cannot achieve your desired conversion. Okay, so we are done for CSTR in series. Okay, so I do not think it's that difficult, but of course, knowing the formula is also important. So maybe now that you are still new, you find it a bit confusing, but later on you will realize that you keep using it, so it will be easier for you. Okay, so I go to the next one. Right, next one is 2 PFR in series. So I'm slowly getting you to do single, then we go to PFR. Okay, so now we're doing 2 PFR in series. So CSTR, I think, is quite straightforward because the formula is given to you, you just substitute. But PFR is not so straightforward because remember, we use Simpson one-third rule, and I will only provide you the general Simpson one-third rule. So you understand, right? The numbers is will change according to your conversion given. So you have to really understand how the equation changes with the conversion given to you. So let us try this question. So the question says, 2 PFR in series and intermediate conversion 60%. So now my X1 is 0.6 and final conversion 80%. So my X2 0.8. So remember, intermediate and final conversion, intermediate are the conversions in your reactor before the last reactor. Final conversion is only for the very last reactor. So you may have more than one intermediate conversion, but there's only one final conversion. So in our question here, X1 0.6, meaning first reactor, they are converting from 0 to 0.6. My second reactor are converting from 0.6 to 0.8. That's the part you must really remember. Second reactor are converting from X1 to X2. First reactor is from 0 to X1. Okay, so how do we solve this? Right. So let us go the first reactor. So the first PFR, it's always wise, in my opinion, to write down the integral formula, because when you write down the integral formula, then you will know your bottom limit and your upper limit in your integration. Okay, so the volume PFR 1 equals to FA naught, integrating from 0 to 0.6, because my first reactor, they are converting from 0 to X1, 0.6. dx per minus RA. So then the integral part, you will convert into Simpson 1/3 rule. So the FA naught stays, then becomes the delta X per 3. Okay, we will discuss how do we find delta X per 3. But most importantly is the 3 points behind. So you know that I have 3 points because the first point is for my bottom limit. The third point is for my upper limit. The middle one is for my middle limit, which I have to find by myself. Okay, so the first one will be 1 per minus RA when my X is 0. So when my X is 0, I will check from the table what is my minus RA value. My last point is 1 per minus RA when my X is 0.6. Okay, so again, check from the table, when my X is 0.6, what is my minus RA and the middle point. So this is the point that you have to determine by yourself. What will be my middle point? So if I have initial X of 0, my final X as 0.6, therefore my middle X will be 0.3, middle point, right? So the middle value will be 4 per minus RA when my X is 0.3. So you have to first know your middle X, and then you find the minus RA at your middle X. Again, I repeat, you have to first know your middle X, and then you find your minus RA at your middle X. Okay, so you can now check the table. So we go back to the first table. So at my X0 minus RA 0.053. When my X is 0.3, my minus RA is 0.045. When my X is 0.6, my minus RA is 0.025. So you will replace everything into the equation as I'm highlighting right now. Okay. All right, then next one, I have not yet explained on the delta X. So again, delta X is the difference between initial X to middle X or middle X to final X. Your initial X is 0, your middle X is 0.3, the difference is 0.3. Or let's say you want to do from middle X 0.3 to final X 0.6, the difference is still 0.3. So your delta X is 0.3. So you replace all the value, you calculate, you will get the volume as 517.15 dm cube. So that's the volume of your first PFR. Okay, so first PFR is not that difficult because your bottom limit is still 0, right? But the second PFR is when you may get confused. So I keep repeating, you have to really understand how the formula changes. So for the second PFR, now the integration will be volume PFR2 equals to FA naught, but now the integration is from 0.6 to 0.8. Again, the integration for the second reactor PFR is now from 0.6 to 0.8 because second reactor is converting from x1 0.6 to x2 0.8. Okay, so let's say you put the wrong bottom limit or the wrong upper limit, definitely your Simpson one-third rule will be wrong as well. So I highly encourage you to write down first the integration part so that you can already determine your bottom limit, your upper limit. Okay, then let us go to the Simpson one-third rule formula. Okay, so delta x is still the same. FA naught is still the same. Delta x per 3 is there. We will discuss later how to find delta x per 3. But let us focus on the 3 point behind. So the 3 point behind is the one that you cannot do the mistake. So the first point will be 1 per minus RA at my x1 or my bottom limit, which is x1. So our x1 is 0.6, right? So it's 1 per minus RA when my x is 0.6. Okay, it's my minus RA when my x is 0.6. So my third point first. So the third point will be 1 per minus RA at my x2, which is 0.8. Okay, then only you look at the middle point. So you have to know the middle one. So the middle one again is 4 per minus RA at my middle x. So your initial x was 0.6, your final x is 0.8, your middle x will be 0.7, right? So you have to know by yourself. Initial x 0.6, final x 0.8, middle x will be 0.7. So you become 4 per minus RA when my x is 0.7. Okay, again I repeat, when I put 0.7 here is to inform that it is minus RA when or at my x 0.7. It's not multiplied by 0.7. Okay, right. So all this value you can check back the table. The values are provided by the table, so it's not problem for you to find the value. But let us go towards delta x per 3, which is very likely some student will make the mistake. So how do we find delta x? So again, delta x is the gap, right, between bottom to middle or middle to upper. So your bottom was 0.6, your middle was 0.7. So the difference in the gap is 0.1. Or let's say you want to go the last part. So the middle was 0.7, your final was 0.8. So the difference is still 0.1. So that's why your delta x is 0.1. So then you replace everything inside. FA naught is still the same. You replace everything inside, refer to the table for the information. You will get the volume of the second PFR as 395.67 dm3. Okay, so that's the volume for the second reactor. And then that's how you solve the question for the PFR. Okay, so we are done for question number 1. I can probably say it's not that difficult, okay, but knowing the formula and knowing how the formula change according to the question is also important, right? So I will give you again another 1 minute break. I think CSTR no problem, right? Okay, I will share the screen for this PFR. I will give you about 1 minute break. I will come back and we will continue to the next question. Okay, right. right? Okay, so we will go to the next question. All right. And let me check. All right. Okay, so today we will just continue with another question. So we are done for today. So tomorrow I will continue the next question. So I did not want to go too much also at one time. Okay, so the next question will continue next tomorrow. I will just finish this one question number 2, because question 1 and 2 is using the table. Question number, we have how many questions? We have question number 3, number 4, number 3, number 4, number 5. Hold on. We have 7 questions. Okay, so the rest is using plot. Okay, I have more questions for the plot. I have only 2 questions using the table. Okay, let us go to the question. Right, sorry. Betul ke? Saya check. Let me check. So I updated the question. Then I forget how many questions we have. So we have, sorry, 1, 2, 3, 4. We got 5 questions only. 1, 2, 3, 4. Yeah, we got only 5 questions. Correct. I didn't have until 7 questions. 5 questions. All right. So 3 questions on the plot, 2 questions using the table. So I will cover all the table 1 today, and we will cover the plot 1 tomorrow. Right. Okay, so last question. So before I forget, for the class tomorrow, we will start at 9, and although in the schedule lab time 8:30, right? But I think 8:30 is a bit too early for everybody, including myself. So tomorrow class we start at 9. So you have extra 30 minutes for you to rest. Then we will start the class at 9 o'clock. I have already sent the calendar invitation. Make sure you check the calendar invitation. I follow your lab schedule, okay? So please check if you are not invited for the correct time, although you are in that lab session, you please inform me because I follow the ECT according to your lab schedule, right? Okay, but if you are not invited, but you're supposed to be that time, you just inform me, I will include you. Or let's say you want to swap, I give you option. Let's say you do not want to attend Tuesday class, you want to attend Wednesday class, you also can do so. Just give me your email address, inform me. You can also swap. I give you the freedom to choose either Tuesday class or Wednesday class. It's okay for me. Right, okay, so let me go this question. Okay. A mixture consists of pure A and just the reactor. So again, the question, I only have 1 reactant, I have 2 product. Okay, so the question gives you again the table, right? So this table is understandable. We have already done a few questions using the table. So it should be no problem for you to understand the table. However, let us understand the question. You can see here, the question is becoming longer and longer. Okay, so as the question becoming longer and longer, the challenge is to understand the question. So the question say, in the plant, they are available 250 dm cube. Sorry, they are available 250 dm cube CSTR reactor or 250 dm cube PFR reactor. Okay, so in my plant now, I have 2 PFR and 2 CSTR. All 4 has equal volume of 50 dm cube. So imagine your plant now, I have 4 reactors. All reactors are 50 dm cube volume. So VCSTR1, VCSTR2, VPFR1, VPFR2 are all 50 dm cube. Okay, so they say to achieve higher overall conversion of A, the technologists decided to use either one of the reactor in series. Okay, so they say now that for you to achieve the conversion that you desired, you now have to decide, should I use 2 CSTR or I use the 2 PFR? Okay, so the question says, it's targeted that the intermediate conversion can be achieved at 20%. So your X1 is 20% or 0.2 and overall conversion 80%, 0.8. So your X1 0.2, your X2 0.8. So now you have to decide, if I want to achieve X1 0.2, X2 0.8, I have to decide, should I use the 2 CSTR or the 2 PFR? Okay, so let us further get information. This is initial flow rate of 1.5 mole per second. So again, I always tell you, when you have numbers, check the unit is mole per second, mole per time. So mole per time is molar flow rate. And they say initial flow rate. So it's initial molar flow rate. And then you realize in your equation, chemical equation, there's only one reactant. So definitely it's the initial molar flow rate of A. Okay, so again, it's initial molar flow rate of A because they mentioned initial flow rate. Then there's only one reactant, it's definitely A. So your FA naught is 1.5 mole per second. So that's all that I have the information. So this says, evaluate which reactor configuration can be used to achieve the targeted conversion by comparing the calculated and available reactor volume. So they ask you to evaluate which reactor that you want to use, 2 PFR or 2 CSTR. And the decision must be based on the comparison between your calculated volume and the available reactor volume in the plant. Okay, so the gist is that you have to make sure that when you calculate the reactor volume, it must be equal or smaller than the reactor available. But if you calculated the volume is higher than the available reactor volume, then the reactor cannot be used. For example, let's say when you calculate the reactor volume needed is 20 dm cube. And in your plant, the reactor is 15 dm cube. So your calculator is more than available. You cannot use the reactor. But if your reactor calculated volume is smaller than available reactor volume, that means you can use. So meaning what you need to do? You have to calculate the reactor volume for CSTR1, CSTR2, compare with the available one. Calculate volume PFR1, volume PFR2, compare with the available one. Okay, so let us go to CSTR first because CSTR is always the easiest one, right? So for CSTR1, the volume is given equation FA naught X1 per minus RA at my X1. Okay, so my FA naught is given as 1.5. My X1 is 0.2. So remember, in my first reactor CSTR, they are converting from 0 to X1. Okay, so my X1 is 0.2. And when my X is 0.2, my minus RA is 0.050. So that's why you need the table. The table will give you the information. When my conversion is 0.2, my minus RA is 0.05. So I substitute in 0.05. I get the volume of my first CSTR as 6 dm cube. So again, you compare the available reactor, the volume is 50. But you only need 6. It's much smaller, right? So meaning the first CSTR can be used because the volume that you need is smaller than the available reactor volume. So CSTR1 can be used. So let us calculate CSTR2. Okay, so CSTR2, the formula is now given as volume CSTR2 equals to FA naught in bracket X2 minus X1 per minus RA at X2. Okay, so kalau if the first reactor minus RA at X1, second reactor is minus RA at X2. FA naught is still the same. Okay, regardless you're calculating for the first reactor, second reactor, the FA naught is still the same. That's why our conversion will increase, continuously increase. Okay, so FA naught is 1.5. X2 is 0.8, X1 is 0.2, and when my X is 0.8, my minus RA is 0.013. So I will replace 0.013, meaning at my X 0.8, X2, my minus RA is 0.013 from the table. And when I calculate, I get the volume as 69.23, meaning to say that if your second reactor, you would like to achieve the conversion of 0.8 from 0.2, you need the reactor volume to be at least 69.23. However, remember, the information says in your plant, the reactor volume is only 50 dm cube. So your reactor volume needed is bigger than available reactor. So CSTR2 cannot be used in your configuration. So since although CSTR1 can be used, CSTR2 cannot be used. Therefore, we can conclude that the CSTR in series cannot be used because you cannot only use one, you must use both. But the second reactor volume is bigger than the available one. Okay, so since we cannot use reactor 2, we cannot use the CSTR configuration. Okay, so that's for case of CSTR. So we repeat back for PFR. We compare again. Can we use PFR instead? Okay, so For the first PFR, okay, again using Simpson one-third rule, for the volume of PFR1 is equals to FA naught integrating from 0 to 0.2 because the first reactor are converting from 0 to x1, which is 0.2 dx per minus RE. Then we convert into the Simpson one-third rule. It becomes FA naught delta x per 3 in bracket 1 per minus RA when my x is 0 plus the last point 1 per minus RA when my x 0.2 and the middle one will be 4 per minus RA when my x 0.1, the middle x, right? Because your initial x is 0, your final x is 0.2, your middle x is 0.1. So you become 4 per minus RA when my x is 0.1. Okay, then again, all this minus RA value, you just check from the table. So when my x is 0, what is my minus RA? When my x is 0.1, what is my minus RA? When my x is 0.2, what is my minus RA? You can get all this from the table, but let us focus on the delta x. So again, delta x is the gap between initial 0 to middle x 0.1 or middle x 0.1 to final x 0.2. Either way, the gap is still 0.1 for your delta x. So you can replace with 0.1. So when you solve this equation, you will get the volume as 5.79 dm cube. Okay, again, our available reactor volume is 50. Our needed calculated one is just 5. Okay, so the one available is much bigger than what you have. So definitely you can use, okay, because the 5.79 that you calculated is the least amount of volume that you need. Okay, so meaning that your reactor must be at least 5.79 or bigger than 5.79. So in this case, you have a bigger one. So PFR1 can be used. So again, let us check PFR2. Okay, so PFR2, the formula now, integration become volume PFR2 equals to FA naught, integrating from x1 0.2 to x2 0.8. So again, PFR2, they are converting from x1 to x2, 0.2 to 0.8. Now you convert into Simpson one-third rule. So Simpson one-third rule becomes FA naught delta x per 3, 1 per minus RA at my x1, 0.2, sorry. My last point is 1 per minus RA at x2, 0.8. And then the the middle point you have to find. So you have 0.2 is your initial x. Your final x is 0.8. Your middle x is actually 0.5. Okay, if you're not sure, you can use method, you can calculate. Initial 0.2, final 0.8, your middle x is actually 0.5. That's why the middle point becomes 4 per minus RA when my x 0.5, the middle x. So remember I told you the equations are provided, but you have to really know what is my middle x, what is my initial x, what is my final x. So this is the one that will change according to question. Okay, so now that you have determined minus RA at which conversion, your next step is to find the value from the table. So when my x is 0.2, what is my minus RA? When my x is 0.5, what is my minus RA? When my x is 0.8, what is my minus RA? All can be obtained from the table. Then next one, delta x per 3. Okay, so this is the one that, again, you may do mistakes if you forget the concept. So the delta x is the gap between, in this case, x1 to middle x or middle x to x2. So your initial x, your x1 is 0.2, your middle x is 0.5. So the difference is 0.3, right? Or the back, middle x is 0.5, your final x is 0.8. The delta x is still 0.3, the difference, right? So therefore, your delta x is 0.3 divided by 3 because the formula is delta x per 3. So when you do the calculation, again, you have to do the calculation by yourself. Okay, hopefully later on when you have extra time, then you will get the volume as 32.72 dm cube. So again, in order for me to achieve the second reactor conversion from 0.2 to 0.8, my reactor volume must be at least 32.72. So if you remember, your plant available reactor volume was 50. So definitely the volume available is bigger than what you need. Therefore, the PFR2 can be used as well. So in the case of PFR in series, PFR1 and PFR2 can be used. Therefore, we can conclude that the PFR configuration can be used. However, why we cannot use CSTR? Because although the first CSTR is fulfill the requirement, the second CSTR does not fulfill the requirement. So you cannot use the CSTR configuration. So that is how you answer the question. Okay, so you can see question number 2 is no longer straightforward. Okay, they do give you certain hint what you need to calculate, but you have to answer the question. How do you evaluate? So you evaluate based on the reactor volume, the available one, and the calculated volume that is given to you. Okay, so that is all for today class. I do not want to go further. I will continue tomorrow. So again, for those LO1 P1, I think tomorrow your class is 9 o'clock. So those LO1 P2 is on Wednesday 11:30. Okay, so but it's only 2 hours. Okay, so 9 to 11 or 11:30 to 1:30. Okay, I will finish the tutorial questions by tomorrow and Wednesday. So if you already have the calendar invitation, if you are not invited at the correct schedule, please inform me. Or if you would like to swap also, please inform me so that I can put the calendar invitation accordingly. So today's video, I will also download and I will upload it on VLE, hopefully by today or at least by tomorrow morning should be ready. Okay, so that's all for class today. I will see you tomorrow and Wednesday.